So what I'm going to talk about in this lecture is really all of physics, actually, all of the known physics at the moment, plus a lot that's guessed. And so the lecture is going to be even more extensive than the ones before, because there I was only dealing with 2 particles, and now I have to deal with, I guess it's 24 particles. But first, I'm going to divide this talk into 2 parts. First, I'm going to talk about questions that are directly related to quantum molecular dynamics of itself, supposing that that was all there was in a system, electrons and photons, what problems are associated with that theory alone. And the second set of questions has to do with what is the relation of this stuff to the rest of physics, to nuclear physics, gravitation, and so on. So start with problems of quantum molecular dynamics, which I suppose now that the theory is completely understood and you know what I'm talking about because you were here at the other 3 lectures. Most shocking characteristic is this crazy framework of amplitudes, and if you would think about there being problems, you're sure that problems must be associated with that. But the physicists have been fiddling around with this now for 50 years, and we've gotten very used to it. A. B. All the new particles, all the new phenomena having to do with nuclei and higher energies, etc., always turn out to fit perfectly with everything that you can deduce from supposing it's a framework of amplitudes whose square is probabilities, then interferences and so on all appear. So that the model structure of the world, the framework of the world which I described, has no experimental doubt about it. You can have all the philosophical worries you want, but there we are. Because it's an experimental science, we have no other way to go. There's another set of problems, which are technical problems, having to do with improving the method of calculating the sum of all the amplitudes. You make all these pictures, and you have to add all these numbers, and you have different kinds of techniques that are available in different circumstances. And, of course, that is what the graduate student learns how to handle and what takes so long to learn. And, of course, since it's so technical, I'm not going to discuss it. That's just a continuously improving techniques for analyzing what quantum molecular dynamics really says in different circumstances. But we have one additional problem that's characteristic of the theory itself, we have a particular problem, a characteristic of the theory itself, which as a matter of fact was the reason why it took 20 years from the time it was first invented in 1929 till the time it was first satisfactorily used in 1949. And that has to do with this problem. We have in our theory, for example, if we start with an electron here, we have a certain amplitude that it gets to here, which we can supposedly calculate first by supposing it goes directly, and that amplitude is a direct function, a very precise function that comes from relativity that contains a particular number in it, which I wrote last time as ME. And I'd like to write this time as M sub in. And we put in to the theory. We have to just put it in and then find out what results we get and find out what number we have to put in there to agree with the experiment. This is the amplitude that a particle starting at 1 will get to 2. I think I wrote it this way last time. And depends on the mass of the object. However, the real amplitude to go a long time from position 1 to 2. I also told you last time that the amplitude was constant in space, and you added this all together, then you'd find that the amplitude to find it at a time 2 simply rotated at a certain angular rate. The angle would keep turning at a rate depending on the mass, m. But in fact, there is the total amplitude to get from point 1 to point 2 also contains other possibilities, of which this is one, that the electron could have emitted a photon and reabsorbed it. And the electron could have emitted 2 photons, or a photon twice and reabsorbed it, and a whole lot of other diagrams that you keep on going. Contribution from these various diagrams, if this one, for example, is of order c squared, where c is a number that goes every time there's a junction, or called a coupling, and c squared was equal to 1 over 137.03599 and so on. We haven't done it experimentally. We're not sure of this within a 3, plus or minus 50. And that's determined also experimentally so that the predictions of the theory agree with experiment. Now, the thing that's I'd like to emphasize is that because of the other amplitudes, the real total amplitude to arrive at the time 2, supposing, let's say, that initially it was equal amplitude to be everywhere in space, does not revolve, the phase does not turn at exactly the original value, but turns at a different value because of the contributions of these other values. This one would go around at this rate. The angle, the amplitude to arrive is a complex number, which with time t2 changing, goes around. After you've added these, it's again a complex number, but it goes around faster or slower, different rate. Now what we measure when we measure the mass of an electron is in an experimental world is the rate that it goes around. The mass of an electron is its energy. The mass and energy are equivalent, as Einstein showed, and energy is equivalent to frequency, as I guess it was de Broglie showed. And so I keep saying mass and energy and frequency interchangeably because I'm so used to that. At any rate, the frequency or the mass or the energy of the electron, the one that we're going to measure experimentally is not the one we put into the theory. So we have another mass, which is the mass experimental, which we could see would be expected to come out something like this. If the c-square was small, very small, and you want to forget it to 1%, forget that 1%. This term is of order c4. You would say first approximation comes from this amplitude, you'd get something like that. And then you'd have a correction because of this thing, which would have a c-square times it. In other words, some correction with 101%, something like that. A correction that you'd compute by adding these diagrams together, and then maybe c4 times another correction from this, and so on and so on. That's easy to understand. Now, when we make calculations of any other physical result, it's much more convenient to express the answer in terms of this m, which is a measured value, than it is in terms of that. So we have a habit of writing all the answers. Always imagine we might start with a number like this, calculate everything, and express everything in terms of the experimental mass that we measured, which is the sum of all these things. So all answers are calculated in terms of the experimental mass. Now, if you've understood me at all, you probably don't understand why we made such a big fuss of that, because that's just a matter of convenience. It's just a question of whether I put it in here and compute that, put it in here, or whether I put it in directly. The difficulty is, and the peculiarity, the thing that bothers us, is that this correction that you multiply c-square by is infinity. And the fact that it comes out infinity because this function and the one for this was the electron one, and for the amplitude that the photon gets from here is the same from here to here, this point to this point, actually, not 2 to 1. I shouldn't have said that. In here, we're just going from here to here. That multiplied by the same function for zero mass and then added everywhere comes out infinity. And that caused a lot of trouble for the first people who invented this theory. They saw they were getting infinity for every answer. Because at every problem that they did, there was something like this in it somewhere. An electron going from one place to the other would always be possible to emit a photon and absorb it. Every answer to every problem was infinity. It was noticed by 1949, 20 years later, it was noticed by Beta and Weizsäcker that if the answers were put in terms of M experimental, it looked as if, in spite of this being infinity, when you wrote the answers in terms of that and computed them, there was no infinity. All the infinities canceled out. So that if you had expressed the answer in terms of the final M and not in terms of this one, then everything would be finite. It looked that way, and it was just a matter of checking out that, in fact, that was true. That's what was done by Schwinger and Tomonaga and myself. I got prizes for that. But one way you could say all this is that this number is unavailable experimentally. It doesn't mean anything. You put it into a theory. Let's, for a moment, imagine that, so that whatever this is, I can always adjust this number so this comes out finite. If this is infinity, I put minus infinity in for that. And that's one way of saying what we ultimately are doing. Although this looks like it comes out in infinity, we put minus in, this comes out, let's say, not infinity, 10 billion, right? Then we put in 9,999,999, only get 1. So if this, or whatever this is. So the idea is if this goes toward infinity in a calculation, we just say, well, just keep on adjusting the m so that it's to fix it back so that the m comes out finite. Now you laugh at that. because you have some kind of a feeling that's a dippy way to do mathematics, and it is. And this dippy way to do mathematics is the way we do this theory, because we don't never been able to straighten it out. But we do know that if we do this dippy way, we get results which agree with experiments. If it had been that this correction were finite, there would be no problem, of course, because the fact that this would be some number and there would be another number. But this fact that the correction is infinite is very annoying. And as a result of that, it has turned out it is not possible to prove at the present time that the entire theory of the quantum electrodynamics that we've written down is really self-consistent, that there's not some, if we calculate everything extremely accurately, we wouldn't get into some difficulty in itself, that the mathematical structure of the theory is self-consistent. There's a nervous condition that there's something wrong with the need that we start with a nice number and have to put minus infinity and play games like this. That annoys us, okay? So that there's one problem, what I have to say, is that in this, although this calculational scheme is quite definite and we know exactly what to do, this process, which is called renormalization, we are not satisfied that it's a mathematically legitimate process. But you notice that when we compute the 10 decimal places, it agrees with experiment. So it may be all right and may be a real theory. Another way to describe this business is the following. In making all these calculations and adding over all possible places for the, in this case, there's a contribution. 1 and 2 is here, but in our problem where I'm having trouble, let's call this 3 and 4. Then we would have this at 4 and this at 3, multiplied by the photon going from 4 to 3, which is the same thing at 0, man. And when it turns out that when 4 and 3 are very close together, that these both things rise together as get close together, but so much that when you add all the possibilities, you get infinity. So one way of saying this is, your whole idea that you can have 2 points infinitely close together is nonsense. Your whole thought that space can keep on going down to the last notch and you can use geometry to the very last infinitesimal distance is wrong. Suppose we stop these sums when 3 and 4 are closer to some very tiny distance. Let's say a distance that's shorter than any distance or any wavelength or anything we're able to get experimentally. Then this correction comes out quite small. Well, it depends. If you make the distance sufficiently small, then the correction gradually builds up. In order to make this correction term equal to this, so that this has to be 0, sort of, it turns out that the distances that you have to use are absolutely, well, I can't even, it's no use trying to describe them. They're like 10 to the 100 power or something like that, 10 to the minus 100 centimeters, whereas all we can do experimentally is 10 to the minus 15. That means some, I don't know, 80, 90 decimal places further on than where we are. So it's always possible that nature's different 5 or 10 decimal places down. 20 decimal places down. You don't like it 30 decimal places down? It's all right. The trouble is that we cannot make a model of that, a real model. If we stop these things at some distance, then the theory that we write is mathematically inconsistent. It gives probabilities that don't add up to 100%, or it gives negative energies, or it gives something silly. Of course, it gives these things with infinitesimal amounts, but it's not a self-consistent theory, and therefore we don't know. We do have this difficulty with this theory. We don't know whether if we stop the theory temporarily, it makes sense, or if we just go taking what we call the limit here, where we use everything and do the renormalization process, calculate everything in terms of the experimental mass, and then forget about the infinity, whether that's a mathematically sound thing. So I have to explain that in order to tell you the exact position of physics today. That's the problem. It turns out, in addition, there's the same kind of a problem about the sea. That also has a correction. If you were to have started out and imagine that 2 electrons were interacting via a photon, and they were an effective coupling C0, C0. And now you have a correction, because the photon that goes along can make a pair, and then that could annihilate and make another photon. And that corrects this, and so on. And in exactly the same way, the effective coupling constant, which is measured experimentally. See, I cheated a little bit. I said it was that. It isn't. It comes out like this, that the experimental coupling constant is equal to C0 square plus corrections of the order C4. See, because you have 2 C's here and 4 C's here times a correction. Yes, you guessed it. That's right. This correction is also infinite and causes us the same nerve-wracking business. But this is measured experimentally. Make that 0, and it'll come out okay, because 0 times infinity is finite. Never mind all that. If we put the results in terms of the experimental constant, then there's no difficulty, and all the infinities disappear. So in other words, we have to use the renormalization trick twice, once for the masses and once for the charges. Once for the coupling constant, which is called electric charge, and the other for the mass of the electron. Okay? And when we're finished, we get a coupling constant, which we have to look to experiment to measure. So that is simply a technical difficulty, perhaps, and maybe a real difficulty. But anyway, that's the slightly discomforting condition in which the theory is. That's the first main problem. Now, with regard to questions about electrodynamics, if you say, I accept that, that probably is okay, or if it isn't okay, I'll wait for some mathematician to find out for me. We then have the following interesting physical problems I mentioned before. Where does this number come from? From experiment. I know, but a good theory would have that this thing is equal to 1 over 2 times pi times the cube root of 3 times 6 and so on, so that you know what it was, if you know what I mean. It's a number that has to be put in, that nature has, or so to speak, if you're religious, you would say God has created that number. But we would like to try to figure out, if we can, a little clue as to how he thinks to make a number like this. For example, maybe why isn't that a 4 there, you see? Okay. In the same way, by the way, you might ask, in the same way, what is the mass? That is also a number. Yes, that's also a number. If you write the mass of the electron, and I'm always going to put the experimental masses down, it comes out a number. There's so and so many grams. And why is it that many grams? You first have to tell me why a gram is as big as it is. It's because somebody chose a gram, I think during the French Revolution or something. They decided such and such is a gram, and then the electron is so many grams. That's therefore not a real problem. But nevertheless, I'll put it down here as a problem. I'm not going to use grams because there's too many zeros. We have a particular unit which doesn't make any difference what it is, but we'll call it the million electron volts. It's the energy, masses and energies equivalent, that you get when you have a million volts and have one electron fall through that much difference in voltage. And this mass is known many more decimal places, but I'm not going to bother you anymore with these long strings of numbers. So the mass of the electron is this, and of course we don't know why it's that particular number. That depends on why we chose the gram, the size of or the electron, the volt, the size it is. Okay? And so that is not by itself a serious problem. But the reason I write it down is that it's going to turn out that there's a large number of particles in physics, not just electrons. There's, as I mentioned, several dozen. And they all have masses, and they're all different. And they're all the same problem. Where did this one get its mass? They're all relative to it. You can't play games with the grams anymore. One's a ratio. For example, you find one is 67 times this one. Why? So the masses are, in general, a problem, to which we do not know the answer. So we have no way to determine this mass. Now, that summarizes all of the problems associated with quantum electrodynamics. The most beautiful one is the coupling constant 137 point and so on, and all good theoretical physicists put that up on their wall and worry about it. There is, at the present time, no idea of any utility for getting at that number. There have been from time to time suggestions, but they didn't turn out to be useful. They would predict that the number was exactly 137 when it looked, well, the first idea was by Eddington, and experiments were very crude in those days. The number looked very close to 136. So he proved by pure logic that it had to be 136. Then it turned out that the experiment showed that was a little wrong. It was near 137. So he found a slight error in the logic and proved with pure logic it had to be exactly the integer 137. It's not the integer. It's 137.036 6-0. Every once in a while, someone comes out and they find out that if they combine pi's and e's and 2's and 5's with the right powers and square roots, you can make that number. It seems to be a fact that's not fully appreciated by people who play with arithmetic, that you'd be surprised how many numbers you can make by playing with pi's and 2's and 5's and so on. And if you haven't got anything to guide you except the answer, you can always make it come out even to several decimal places by suitable jiggling about. It's surprising how close you can make an arbitrary number by playing around with nice numbers like pi. I mean, and therefore, throughout the history of physics, there's paper after paper of people who have noticed that certain specific combinations give answers which are very close in several decimal places to experiment, except that the next decimal place of experiment disagrees with it. So it doesn't mean anything. Okay? Those are the problems of quantum molecular dynamics. Now the next part is the connection of quantum molecular dynamics to physics, to the rest of physics. And then we're going to have a good time now for the rest of the lecture because I'm going to tell you all about the rest of physics. And you can compare the laws of the rest of physics with the laws of quantum molecular dynamics. But first I must say immediately that the rest of the laws of physics are not known as well as quantum molecular dynamics, and therefore what I have to say is to a varying degrees uncertain, nowhere near as certain as the electrodynamics. So first there must be a connection because we have to discuss one point. The photon, which couples to the electron, also couples to the nucleus. That's why the electron is attracted to the nucleus. So there's something inside the nucleus that couples with a photon. In other words, we sometimes say it's charged. To say a particle is charged or something is electrically charged is merely a statement that it couples to a photon. A photon is absorbed by it or emitted by it. That's what it means. Anyway, nuclear particles are charged. So in the beginning of the history of this thing, knowing about the nucleus and puddling around looking at them, it became pretty clear that it's easy to understand nuclei of the atoms, that tiny little center where the electrons go around. They're different from atom to atom, and they can all be thought of as being made out of two particles, a number of particles of which, how do you say it in English? A group of particles which are either protons or neutrons. Like, for instance, a particular carbon, for example, is a nucleus that has 6 protons and 6 neutrons in it. Nuclei can have, uranium has 146 neutrons and 92 protons in it, and so on. Hydrogen, the simplest nucleus, has just 1 proton in it, and so it goes. So out of protons and neutrons, the nuclei can be made. But the protons and neutrons that are in the nuclei stick together quite tightly. The forces are very large. The energies that are released when you let them jiggle around are much greater in proportion as the atomic bomb is more effective than dynamite. Because the dynamite represents a rearrangement of the electron patterns, and the atomic bomb represents a rearrangement of the proton-neutron patterns. And the relative energies are very large. The particles that interact, when we tried to, at first guess would be that the proton is simple also, and that the propagation of a proton, that we make diagrams for protons, same way, and all we have to do is put the mass of a proton in here. Problem, first. It must be that there's more than just photons involved because the forces in nuclei are stronger than electrical forces by about 100 times. If we would invent some new force, we would have to have a kind of a c-square of the order 1, not 137. Because the size of the forces needed are 100 times bigger than electric forces, we call those strong forces. Strong forces are those in which somewhere there's a constant of coupling closer to 1 than it is than electricity. I mean, it might be a quarter, it might be a fifth, it might be 2, but it's not 100, not 1%. In investigating this, at the beginning it was hoped that the proton was simple, but the proton kept on showing that it wasn't simple at all. For example, there's many properties that indicate that it's not simple, and the neutron is not simple. For example, the proton, the electron, we talked many times, has a magnetic moment which we can start expanding like this. But the proton has a magnetic moment 279, completely crazy. And the neutron, which is neutral and should have no magnetic moment, no magnetic interaction at all, if it were really neutral, is in fact has a magnetic interaction, which is some number. 3. That indicating that inside the neutron there were some charges that could interact magnetically. It might be neutral, but there are plus and minus or something going around in there or something. So to find out more about these particles, which look so much more complicated than the electron, we did many experiments bombarding protons onto the nuclei and hitting them harder and harder, first to drive the parts out of the nucleus in order to see how the nuclei were constructed. But in the process, you discover, going higher and higher energies, that you created new particles. And the names of the new particles go, first they discovered pions, and then muons, and then lambdas, and kaons, and sigmas, and x's, and you ran out of the alphabet. So pretty soon it was the sigma 1190, and a sigma 1386, and a lambda 1190, and so on, because you just gave more numbers, and those numbers were the masses of the particles. And ultimately, it is clear that there's an unending number of particles, there being about 400 and some odd particles at the present time, but it's an open-ended thing. It depends on how carefully you measure. You can't go along with 400 some odd particles. Things get more and more complicated. But then it was realized that these particles can all be understood, cannot all really be understood. We don't know, because now we're moving into partly the unknown. We expect that they all can be understood as being made of others. Now I would like to discuss these others, the so-called, the present guess as to the fundamental particles. Most of the things that are made by bombarding protons and so forth together are supposed to be made of quarks, and I'll tell you about those soon. Those are the strongly interacting particles. But in the process of the experiments, some new particles were discovered which were not strongly interacting with nuclei. The electron, for instance, does not strongly interact with the nucleus. It only interacts through the photon. It's a charge. It's a small thing. It's always got the c squared. There are other particles which do not interact strongly with nuclei. So what I'm going to do is I'm going to divide all the particles up into two classes, those which do not interact strongly and those which do. All right? The ones which do not interact strongly, they happen to be called by a horrible name, leptons, and the ones which do interact strongly are called by an equally horrible name, baryons. So I start out by discussing the ones which do not interact strongly and which are called leptons. And I start to tell you what they are. Well, the first one in the list is, let's put the name of the particle here. And here we can put the mass of the particle in these nutty units, MeVs. And then, I'll put down an electric coupling, which we'll call charge. The strength of the coupling to the photon. This is the coupling to the photon, in another word. But the unit I'm going to use is 1 for the positron. So the first one is an electron. And its mass in MeV is 511. And its charge to the photon is -1 by definition. It's the scale in which I want to measure, and I use minus because of Benjamin Franklin, who chose to call the electron minus. Okay, so we're stuck with that since 1776. Now, and lots of other things we're stuck with since 1776. Which some of them they're not so concerned as I am. At any rate, I now may continue this list of these particles. We have discovered another particle, which is called the muon, which has a mass of 105.6. It's 206 point, we know it very much more accurately than I'm writing it, times that of an electron, and its charge is -1. It does not have a strong interaction, and your first guess would be that it propagates like an electron, except that in this place where I put the mass, I'm sorry, after I renormalize the mass, this is a renormalized mass, it should just be a different number, and that's all the muon should be, and that's all the muon is. There's nothing different about a muon and an electron that we can find except its mass. It's different. It has a different mass. It's just as if God wanted to try out a different number for the mass. And, for example, the magnetic moment of a muon has been measured and is 0.01165. Well, first, we calculated theoretically because if there was had no strong interaction, no magic, it's just electrode quantum. We use quantum electrodynamics, same kind of diagram, same game, and get this number 0 plus or minus 1. Well, let me get it just right. It's 3, I think, plus or minus 1. You don't really care, but the fun of it is to see how nice it works. This is only the 3 plus or minus 1. That's the calculated value. And the experimental value is blah, 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 blah. 90, blah is being exactly the same. Plus or minus 3. I don't want to write the 100. But this isn't quite as accurately calculated or measured as the electron, but within the calculations and measurements they agree. And this turns out to test the idea that there's nothing wrong at short distances more accurately than the other. Because due to the very much higher mass, that simply means that the amplitudes are changing much more rapidly, by 200 times or more rapidly. And therefore, if anything is wrong with the electrodynamics over a short distance, this is 200 times more sensitive to see that there's something wrong. Nothing seems to be wrong. So our space, that's how we know from this, in fact, that the space is accurate down to distances or frequencies, rates corresponding to 20,000 in these scales. The electrodynamics would be right up to 20,000, as we now know, before there's a serious error. Well, that's kind of interesting, and that produces the problem. Where does it come from? You see, now, if you don't like trying to figure out where that mass comes from, your problem is what is the ratio? Why is this true? Is there another answer, so to speak, to some problem? It's as though you had a quadratic equation that you got in a book, that has 2 solutions. Here it is with 2 solutions, and somehow or other there's one answer and another answer, but we don't know what the equation is that has those 2 answers. I know there's some of you clever kids in algebra can cook up an equation that has those 2 answers, but if you didn't know the answer, you wouldn't know how to write that equation. Now, very recently, within the last year or 2, I think, it sort of gradually became apparent, so it's not exactly a year or 2. First clues were a little older. We discovered there's another one. Mass is this time 1,860 approximately times in these units, which is something like 3,640 times as heavy as an electron. It's twice as heavy as a proton. Its charge is -1. And as far as we know, and we don't know much. First, we know it doesn't interact strongly doesn't interact strongly. Second, it behaves for the few experiments that it does behave. Everything can be understood so far by supposing it's another example of an object which obeys quantum electrodynamics perfectly like an electron with no error. But there is I can't write anything down. We haven't measured any magnetic moments or anything of any accuracy. It's just the beginning of understanding it. All right? Now, obviously, there's another one down here, huh? What you got to do is guess the rule to make these. This lecture is to try to tell you really what we don't understand about nature. We don't understand that at all. That makes it very interesting to be a theoretical physicist because you have these wonderful puzzles. Why does she repeat herself at that 206 times and then at 306.40 times or whatever it is? So, of course, you want me to write down the next one, but I have no more knowledge. At the present time, machines are being built to try to do experiments at higher energy. These are very high energies. And they are designed to look for another one, if there's another one down here, unless that's too far along. If it comes out that one should be at 10,000, we're not going to find it. But if it's at 4,000, we might find it. Okay? All right, that's all. That's all I can say about those particles. Well, I'll say some more. The muon is, in fact, unstable. Otherwise, if it were stable, you would wonder why it isn't in atoms. why you can't have a proton with a muon going around it. You can. There is such a thing as called a mu-mesic atom, in which the mu takes the place of an electron. And its energy levels are all computable and everything by the regular way they do for electrons. The numbers are much bigger. Instead of emitting light, this atom emits X-rays. But those are just numbers, just shorter, higher frequencies. But the thing that's interesting is the muon, oh, by the way, like the electron has an antiparticle, which is a positron with charge 1. That's true of all these particles. Everybody going forward can go backwards in time, like the electron, when it turns around, becomes a positron. The muon is negative. There's an anti-muon, which is positive, and presumably, yes, definitely, an anti-tau, which is positive. Anyway, the muon, which is written as mu minus by make it look nice, disintegrates, and it emits an electron. The muon sits here, and in about 2 millionths of a second, an electron comes shooting out, sometimes fast, sometimes slow. But the conservation of energy doesn't allow that. What really turns out, what careful experiments have shown, that there are 2 additional particles coming out, one of which is called an antineutrino E, and the other one a neutrino mu. So I have to tell you about neutrinos now. So I put those in the same list. We have a thing called a neutrino, or rather more precisely, the electron neutrino, neutrino E, which I write a nu E, because I'm getting tired of writing the word. That's just a symbol, neutrino E. It has a mass, as nearly as we can tell, a mass at rest of 0. It always seems to go along at the speed of light. Its charge is 0. So it doesn't interact with photons. And it doesn't interact with nuclei. If it never interacted with anything, we would never find it. But we did find it, so we have to learn something. Now it turns out there's another kind of a neutrino. There's another neutrino, the neutrino mu. You're not going to get tired of this because you're going to keep piling these things on until you're drugged. There's so many particles. I can't help it. I'm trying to tell you how horribly complex, apparently, the world really looks. And if I would give you the impression that since we solved 99% of the phenomena with electrons and photons, that the other 1% of the phenomena will take only 1% as many additional particles. It turns out to explain out takes 10 times or 20 times this number of particles. Okay, this one also has a mass 0, although, of course, experiment can only measure to a certain accuracy, and I'm not sure. It might be as big as an electron or 2. And charge 0. The tau, what about it? Have another one, neutrino for the tau. Well, I put it in parentheses, things that everybody thinks are there but have not had the slightest experimental information. They don't know whether there's one. And we certainly don't know whether the mass is 0. But we surely know it's neutral because we define it. Anyway, what's in parentheses are good guesses. Okay? Now about these neutrinos. This process is understood this way, by saying a muon comes along here. This is the present view of it. Well, the first way, and it turns into a neutrino, the mu type. Okay? This is time going this way in space. And then, I think maybe this is in the way of people. You're clever. All right, now it's in your way. Okay. And at the same time is produced an electron. Use the square chalk. I've got the round chalk. And an antineutrino. Let's put the arrows forward for the particles and backward for the antiparticles. So the antineutrino would be coming in this way. Okay? And the 4 of them come to a junction. And the theory is, present theory, which works nicely in predicting the properties of this reaction, is that this is done by a wiggly thing like a photon. Eh? You would say, hey, it's like a photon. You put a photon in here and everything's all right. Except a photon can't change the charge of a particle. If the junction that photons satisfy go between mu and mu, not between mu and neutrino. So this has got to be a new particle. And furthermore, the fact that this goes as slowly as it does means that this particle is either coupled very, very weakly, if the coupling is extremely low, or that it's coupled with some more or less reasonable strength, but the mass of this is not zero like the photon. It turns out that the present theory, the one that works very well, made by Salam and Weinberg, is that this object, which goes back and forth here, which is the analog of the photon, has a very high mass. And so we start another list of particles. Let's see, I got all of them here. These are all the leptons. And the list goes on. We don't know where it goes, okay? Now I'm going to make another list. I guess the best place to make the other list is here, which are called bosons, or if you would like better, would be the interacting particles. They are, the first one, how do I do it? I give the name, the rest mass, and that's all I'm going to talk about here. The name is the first one, is the photon. Ah, yes, the photon. Its rest mass is 0. That means the mass that you put into the D function. Now this time we just have to put a different mass in for the D function, so the other particle is called a W. It's a horrible, we haven't got a good name for that, a W boson or something. Or W intermediate boson. Horrible name. Anyway, we ought to get a nice name for this one, which we haven't got. Maybe we should call it a Wynon or something. And its mass is 53,000 expected. It's theoretically calculated by how much mass you have to put in here to make that rate right. Okay? And the coupling constants in here are about the same as the C over there. Like 3/8 of the C or 1/4 of the C or something like that. That is, the constant, though, is just the same kind of coupling as it is to a photon, but the mass is much higher. And that makes that happen at a very slow rate. So it takes 2/1,000,000 of a second, 2/1,000,000th of a second. That's slow. Because as you know, the frequencies we've been talking about have 10 millions and millions and millions, hundreds of millions and millions and millions per second. And this is only 1,000,000 per second. So now this particle, in the particular case that I explained, if you imagine the particle went from here to here, has another property that I have to explain. It turns out that electric charge is never lost. In this particular experiment, the negative electric charge on the mu appears in the electron. But through the intermediary here it goes, and therefore this intermediate is electrically charged. So this thing is charged. So if we wrote here charge on our list, the wrong thing to do is when you get stuck with the wrong colors, then you have to keep remembering which hand has which. Okay, charge. And a photon doesn't interact with a photon, so it's got a charge of 0. The charge means, how does a photon interact? And the answer is, this has -1. Oh, I could use green. I can use green. -1 for the charge. But if this thing, the timing were reversed, and this was a little lower than that, then you would see that this would have to, thinking of it going backwards, would have to have a positive charge. And it's the antiparticle, so that these W particles and their antiparticles are found both with -1 and +1. And in addition, it's been found that there is another W, which is neutral, and that they now form a nice little triplet, but the neutral one has a higher mass, probably, about 70,000 MeV. So we have here, in this theory, we have a thing that looks very, very similar to electrodynamics, in the sense that you make the same kind of diagram, in the sense that the coupling is the same order of magnitude. The only differences are a rule, two differences actually. A rule about the charges, about what you're allowed to couple to, and the fact that you use the mass in here. And one other technical detail, which is very interesting and has a good history, is that the coupling is not exactly the same as electrodynamic. I said in these problems that there are many polarization cases, and the couplings are 1s and -1s and sometimes 0. This one has half as many cases that are not 0. It has many zeros that a photon doesn't have. So it's coupled just a little differently. By a neutral one, that means that there'll be a process like this. For instance, it could be that a neutrino comes along and comes out as a neutrino and hits an electron. It goes out as an electron, and what happens is that one of these W bosons goes across, but this time it's a neutral one. That has been discovered within the last 4 or 5 years. It's called neutral currents for some horrible reason, but it caused a lot of excitement. So we now have this other particle, and what does it couple to? It couples to the neutrino and the mu. In other words, what we have to ask is now, what are the rules that tell you what kind of junctions it makes? Let's take the junctions with the W minus the negative 1. What pairs of particles can go? We already know a neutrino, even a square chalk, a neutrino mu and a mu is a pair of particles which can be on the junction of a W minus. So they belong together. And the other neutrino goes on a junction with the electron. That's why we named them that way. And it turns out, of course, that the tau, well, we're guessing on that. You see, we believe there must be one. It's some people who are very, very unbalanced who might suggest that that's the same one as this, but of course it's almost certainly a different one. Now, it also turns out that, for instance, a neutron, I'm talking about a strongly interacting particle, and I'm not supposed to be able to talk about that yet, I'll come to that in a minute, but a neutron disintegrates into a proton, an electron, and an antineutrino. And that means that something in the neutrons and protons, the quarks in fact, can also couple to the W. And so this list isn't quite finished, and I'll finish it later on in the lecture. These are the pairs of particles which couple to a W particle, and we just have to keep making lists of those. So for every particle, there's a sort of pair, friend, or something that you get from the ones that'll couple with a W minus. So for the electron, there's this, and so it goes. It's a kind of, we don't understand any of this. We just find this out. And if you can figure out what this pattern is all about, then you will have contributed mightily to theoretical physics. That sums up all of the oh yes, one more important thing. Because this is charged, the photon couples to it, and there are diagrams which would be like this, that let's say, like this is going across, you can have another gamma ray coming out of here. Photon. It could be coupled to the W. And it also turns out that the theory is nice and neat if you allow a three junction like this in which a W naught and a W plus and a W minus can all come together like that. So we have this and we have that. And the coupling constant is much the same. Therefore, the possibility exists that the idea that there's one kind of thing, a photon, and another kind of thing, 3W, is not right, that their four belong together somehow. And so the theory of Weinberg and Salam was to try to put the quantum electrodynamics with what's called the general weak interaction into one theory. And they did it. But if you just look at the result that they've written, you can see the glue. What I mean is, it's not a nice job, okay? There is at the present time, it's very likely that it's interconnected. It's very clear that it's interconnected, that they're different aspects of the same thing. But at the present understanding of the knowledge, it's still not possible to see them very clearly as different object case of the same thing. You can make it look like the same thing, but you can see the seam between the things at the present time. It's not been smoothed out yet, so that it becomes more beautiful and therefore probably more correct. But it is part of our theory today that these things belong together, and the reason they belong together in such a way that you can explain the connection between the coupling constant there and the coupling constant there, but that at the present time is not explained numerically. It just has to be measured. All right? That's the end of the weak interactions. We can breathe a sigh of relief. That's a limited number of particles. You're still within the possibility of keeping this in your head. But now, if we start with the protons and the neutrons and hit them together, we get this enormous number of particles. And the nice thing, if I would give these lecture perhaps 10 years ago, I would show you all these particles and make a long list of them. Then my list that's starting here would have 405 objects and so forth, and I'll tell you all about the properties of them. And then I would explain to you that I believe that none of them are fundamental in the sense that they're propagated by one of those nice little formulas where you put a mass in, because they all appear method. Behavior is not like that. But in the meantime, in the 10 years, there's been developed a theory to explain this multitude by supposing that they're made out of other simpler things called quarks. Simpler in the sense that their propagators are simple functions where all you do is change the mass number. Okay? Now this theory, the theory of quarks, is what I must next describe and represents the theory of strong interaction. So let's use this. I see. There are more particles here, you see, but this board doesn't go into here. It goes under, and we can't see it. All right? Now here's a new piece of paper on top of the other one, which are the strongly interacting particles, and I'm not going to list those, but the particles that they're made out of, which are called quarks. And we're going to make a list of the quarks. By the way, I have to say something. I've been leaving out polarization all the time, the polarization effect, and I'm not going to explain it now. But the electron has a different type of polarization than the photon. But all these particles in this list have that type. It's called spin a half, is the technical language for that kind of polarization. And the polarization of a photon is called spin 1, and the W also has spin 1. So this list corresponds to a kind of polarization of spin 1. And this list up here is spin a half, and as it turns out, the quarks are also spin a half. Same, all the same. Now, what are these quarks? What is the story? It turns out that a thing like the quarks come in there are many different quarks, just like there are many different leptons. And they have names, which are so bad, I'm going to give them letters instead of names. The names are up, down, strange, charm, beauty, and so on. Forget it. I prefer to call it U-type, D-type, S-type, C-type, and so on. So instead of giving them long names, we have the following kinds of quarks. A U-type, a D-type, an S-type, a C-type, a B-type, recently discovered. And as we'll go along, we'll see there must be more, almost certainly. And the next letter that we're sure we're going to use when we find it is T. Some idiot named this charm particle, and this one beauty particle, and this one truth particle. And I can't stand it, so I have to my letters. These are then the quarks, and the proton, for example, is supposed to be made out of 2 U quarks and a D quark, 3 quarks inside, going around inside, 3 of them, 2 U's, U types and 1 D. The neutron is 2 D types and 1 U. All right? Now, of the 405 particles that I don't, well, 405, that's silly. The hundreds and hundreds of particles I was talking about before, they go into 2 classes. Those which, when they disintegrate, ultimately end up as a proton at the lowest energy, and that like a neutron does, for instance. And those are all objects which they're called baryons, and they have made out of 3 quarks. So some of these particles are made out of 3 quarks, a certain class. Another class is called mesons, of which pions are an example, are made out of a quark and an antiquark, and that's all we've found. There ain't no 4 quark guys, or 2 quark guys, or even 1 quark guy. What? No 1 quark guy? That would mean that you can't get these quarks apart so you can see one. So far we have been unable to get these quarks apart so you can see one. You can hit those protons together as hard as you want, I mean as hard as we're able to, and the quarks never come out. All they do is move around and produce new pairs and form new groups of 3s and particles and antiparticles. We can't get one separated. As soon as you get one separated, new pairs form in its neighborhood, particle, antiparticle, quark, antiquark, and they group up so that the quark, antiquark pairs are groups of 3. At any rate, the problem is, of course, what holds these quarks together inside a proton? And that force is large. That's what's strong. And that has to be done by another thing. Because the W's are coupled weak and the photons coupled weak, we need something that couples strong. And so I need another color for my chalk. Actually, I need 3 colors for my chalk. But I won't play with the colors right now. We have pictures of what the quarks do inside a proton. For instance, we would say, here's a proton. Let's say, just to make it nice. No, I better not do that. There's a U and a D quark going along. And then, from time to time, there's a kind of photon, but it's not a real photon. It's a different thing. It's called a gluon. You can imagine the level at which the physicists who can call that truth, they can't. Why is it called a glue? Because it's a particle like glue holding these things together, so it's a gluon. And the gluons go across and do various things in here. In the complete analogy to the way the electrons have photons go between them in an atom. And the gluons, then, are the next particle, and why the colors are shifting here, I'm not quite sure, but there are gluons. Okay? And they have a rest mass 0, like photon, and a 0 charge. But they couple strongly. I should put down here, couples to electron, or couples to charge. This one couples to those pairs, and this one couples to quarks. All right? The particle has the same polarization character as the photon, and so on. We just repeated. It just looks like I've just repeated quantum electrodynamics at a different scale with a stronger coupling. It's almost that. It's very close to that. It's almost exactly the same as electrodynamics on a different scale. I would now, I think, I don't know whether it's worth describing exactly the difference. It's rather curious and interesting. And I see I have a little time, so I'm going to do that. Before I do that, I have to finish with 2 remarks. One, we still have to ask, how does something like this happen? And the answer is, it's the quarks which are doing it. It's the U quark which can turn to a D quark, an electron and neutrino, so that inside here, I'm sorry, I got it backwards. D turns to a U, so that the DDU comes to the UUD. Surprising, but you only have to change one of them to do that, because they're moving around. So the D turns to U. So really, this is not the fundamental rule, but the fundamental, damn this, excuse me, square charge, is that the D particle quark can turn into a U quark plus an electron plus a neutrino, and that's pictured by supposing that on that line that we can have the following diagram. Let's see, for some dumb reason, I've caught myself by making all the quarks blue and so on. It's terrible. I don't mean anything by these colors, but this is to remind you it's a quark. This is a D quark turning into a U quark with the emission of a green thing. A W meson, and then going into, I got myself into a pickle, okay? I should have anticipated that I'd get in this difficulty. The colors are just to keep track of different types of particles to help you a little bit. Electron, neutrino. Did I get the sign wrong? Yes, I got the sign wrong. It's neutrino, electron. Oh, yes, in this diagram, it's an antineutrino. That just means this arrow's up there. Well, that's all right. That's clever. You know how to turn that up there. And this is a quark coming in here. So we have to say, in addition, that the W particles couple not only to these pairs, but also to other pairs. And another pair, it involves the quarks. For example, here would be that it was the U quark coupling to the D. All right? This is not quite right. I'll put that there to remind you. Not quite right. This turns out that the C quark couples to the S. Not quite right. and nobody knows what the heck goes on beyond. What's not quite right is, well, I'll say one more thing. That tells us how the W's couple to the quarks almost. There's a slight fixing I have to do. Now, I also say that the photons couple to the quarks. We know that because we know the proton is electrically charged, and if it's going to be made out of quarks, then the quarks have to be electrically charged. Electrical charge means that the photon couples to it. Now, the electrical charge in this case has to add up to 1. The electrical charge in this case has to add up to 0, and the difference between these two must be 1 in order for that to work. Well, anyway, when you get finished, you find that the U's have to have a charge of plus 2/3. In other words, the charge of these particles goes like this: plus 2/3 for the U, and minus 1/3 for the D, and minus 1/3 for the S, and plus 2/3 for the C, and let's see, the B is probably minus 1/3, but now we don't have too much. It's a good guess, so we haven't checked it, but the others are much better understood. And so, of course, the T is no doubt plus 2/3, but that's waiting to be found. Now, with regard to the mass, I cannot really give an answer. There's no way to define the mass because you can't get the particle out separate. And so we have technical arguments as to different ways of defining the mass, and everybody who defines the mass differently comes to different numbers here. So the numbers I'm going to write here are not accepted by everybody, and I won't accept them myself on another lecture when I redefine the way I define it. But for the main feature, I'll define it somehow, and with some particular way of defining it. This is 400, and this is 402. And this one is 500, roughly. And this one is 1800 or 1900. No, 1600. And this is 4500. When they get heavy, everybody agrees with the definition. But when they get light, the problem is the interaction energies are so big that you can't tell how much is due to mass and how much is due to coupling, and it's hard to define it. The feature that we do know is that these two are the same, and this is more. And then when they get heavy, we got the numbers, okay? These are lighter. So that the lightest of all of the strongly interacting particles are made of U and D quarks. Heavier ones involve sometimes an S. For many years, we thought the only kind of quarks we would have were the U, D, and S. By the way, the names of these different, when you want to say different kinds of quarks, you say different flavor quarks. The flavors that we had for many years are just these three, and in 1974, we found a particle called the psi meson, which could not be made out of these quarks. And there was also a very good theoretical argument that there had to be a fourth quark, having to do with that theory over there, the Weinberg and so on. And that's called the C quark. That one belongs with this number. And that checks out, and very, very recently, within a year or so ago, we found another funny particle, which means there has to be another quark, another flavor, all right? And so that, putting down these charge numbers and telling you what pairs couple to the W's and making all these pictures tells you almost the whole theory. The only thing that's not quite right is this. It turns out that the U, which I drew here, let's say the U is connected to a D. The U can also be connected to an S. And in fact, when the U goes through like this, it turns into a D or an S, one amplitude for a D, another amplitude for an S. So that what really happens here is a combination, some amplitude for D, and also some amplitude for S. And in here, it's a big amplitude for D and a small amplitude for S. Here it's the other way, a small amplitude for S and a big amplitude for S and a little amplitude for D. It is very likely that there's some amplitude for B in here also. In fact, there's pretty good evidence that there's a very small amplitude for B, so I could put that in, but it's not known very well. Why it chooses these proportions for those two amplitudes is utterly unknown. So I got everything out. It's a terrible mix-up. And you say, it's a hopeless mess physics has got itself worked into. It has always looked like this. It's always looked like a horrible mess. But as we go along, we see patterns, and we push them back down so that we put theories together. We combine this stuff, and a certain clarity comes, and it gets simpler. It's a lot better than the terrible mess I would have made with the 405 particles a few years ago. The thing that I would finish with, I think it's just as well that I finish a summary rather than to describe in more detail how these gluons work. It turns out there are 8 different kinds and so on. But I'm not going to complicate that. The thing that I would like to emphasize, though, is this: that all these theories are very similar to quantum electrodynamics. They have little tricklet changes, little small counting changes, but they're very similar. They all involve the interaction of a spin 1/2 type object with a boson of spin 1 type object. One case is obscure because it has a mass, but as a matter of fact, all the masses are obscure. So now let me talk now about the grand problem. The character of the theories, forget about the masses for a minute, the character of the theory certainly indicates, well, looks like they're the same somehow. They're very, very similar. But remember something. We have not yet checked quantitatively this theory with the gluons. It might be wrong. We have only got a few experiments to check the W boson. That might be wrong. On the other hand, why does it look like it could be the same thing repeated? There's several possibilities. One, the limited imagination of man. When he sees a certain theory and he sees a new phenomenon, he tries to fit it with that theory, and until he's made enough experiments, he doesn't know that it doesn't work. And so when he gives a lecture in 1979 in New Zealand, he thinks it works, and he says this is the way it works, and look how wonderfully similar they are. It's not because they're similar really, it's because all we've been able to think of is the same damn thing over and over again. Another possibility is that, as a matter of fact, it is the same damn thing over and over again, and that nature has only one way to do it, so to speak, and she keeps repeating her story from time to time. And there's a third possibility. And that is, they look very similar because they're different aspects of the same thing, that there's some larger picture from which is to be understood that the thing breaks down into what looks like different things, but they're different cases of the same thing, not different cases. Well, it's very hard since I haven't got the right theory. I can't exactly explain myself, but I'll try the best to say that there was one large object which has supposedly a first approximation, has a whole lot of fingers, and these are the different fingers. But they all belong on the same hand, and they all got the same characteristics. And the reason, therefore, that they repeat the pattern of having the same kind of interacting particles and the same kind of coupled particles is that they are the same. They really come from the same thing. And so there are many people, of course, working, trying to get the grand picture, which puts all this together in one super-duper model. And I have promised you in these lectures not to talk about speculations, but things that have a reasonable experimental check. None of the speculators agree with any of the other speculators as to what the grand picture is. Throughout this entire story, however, there remains one unsatisfactory feature, and that is the mass numbers. There is no really satisfactory theory of the origin of these masses. We can write this stuff down and we see the pattern, but we don't know where these numbers come from. There are theories which suppose that there's still another kind of particle which generates mass. It has a different kind of polarization. You'll like that one. It has only one kind of polarization, not two like an electron or photon. It's called spin zero. There's proposals that there are spin zero particles in the world and various theories to show how they might produce numbers of masses, but not one of those theories really produces the numbers that we see in a satisfactory way. It just says maybe they will come out, maybe it'll do this, and maybe it'll do that, and the more you look at it, the less it turns out to be the case that it really does what you want it to do. So we do not have any understanding of the masses, and I believe that from the fundamental point of view, that is probably a very interesting and serious problem. The particular work that I work on is this. It turns out that this theory of the gluons and the quarks is a very definite, precise theory. It has only one constant in it plus those masses, the coupling constant. The coupling constant, however, is large. And the method that we use to make calculations for electrodynamics that were successful, easy calculations, in which we approximate by first tidying out the diagram with the least number of these things, and then more and more, because the more you put in, the smaller the contribution because of the 1%. When the coupling is big, the diagrams with many of these and the diagrams with few of them are all important. And the problem is to add everything together in some other order, not just by starting out with no gluons and then putting in one gluon. It'll never work. It is true that at very high energy, in very high energy collisions, it does appear as if it is right to start with an approximation in which you have the minimum number of gluons and make a correction for one more gluon and so on. And in those experiments, you can calculate or predict certain trends which ought to occur, and those trends do occur in experiment, which is the only evidence we have that this theory is on the right track. Because at the present time, although we have a definite theory, we have a situation that's never before existed in the history of physics, we haven't been able to calculate anything from the theory. Therefore, we can't compare it to experiment. It isn't that there aren't experiments. There are hundreds of experiments with the strongly interacting particle, all kinds of experimental accuracy and detail. It's just that we can't calculate anything with this theory, and that's not because the theory is indefinite. We have a definite proposal and a definite result. Let's compare the theory to experiment, the usual thing you're supposed to do. It tells you in books. Science is very simple. You make a theory, compare it to experiment. And if the theory doesn't work, then throw it away. Then make a new theory, compare it to experiment, throw it away. Oh, here's a theory, compare it to experiment. We don't know how. So we're boxed temporarily in making a method of calculation to compare it to experiment. So I'm trying, amongst other people, also trying to figure out how to improve our methods of analysis so we can make a reasonable mathematical analysis of that theory. In all this, I didn't discuss gravitation. The reason I didn't discuss gravitation is this. The gravitational influence between objects is extremely tiny. So tiny it holds you in your seats. Wait. Between microscopic particles, between electrons, for example, or between two muons or protons and so on, the gravitational force is very small. As you know, the force between two electrons varies inversely as the square of the distance and the product of the charges. That's electric force. And this whole gravitational force is the product of the masses and inversely is the square of the distance. And one varies the same way as the other. And one is very much smaller than the other. In fact, the gravitational force, if you don't like big numbers before, you're going to get them now, is weaker than the electrical force between two electrons by one followed by, the factor is 1 followed by 40 zeros, and 41 zeros perhaps. And that's so tiny that you'd say, oh, I will never see gravity at all. The difference is that gravities like attract, whereas in electricity, likes repel and so forth. So when you have a lot of objects, you have a large number of particles. The gravity keeps adding and adding and adding and adding, but the electricity cancels the plus and minuses. So what we end up is that all the electrical forces, which are so enormous between the electrons and the protons, simply hold the electrons and the protons in a terribly intimate mixture of matter. Matter is a fine mixture of plus and minus charges, so fine they all cancel each other out, so on a large distance there's not much left. But gravity keeps on adding and adding and adding, and so at last, when we get to these ponderously large masses that we are, we begin to measure the effect of gravity on planets, on ourselves, and so on. Because of this, from an experimental point of view, it is impossible at the present time to get any experiment in which any quantum question about gravity is involved. In order to produce a gravitational influence, you have to have so much matter, so many gravitons, if there were any, that the quantum approximation is unnecessary. Of course, it is not possible in the world to have this framework of amplitudes on part of the world and not the rest of the world. So it is not a satisfactory situation to say that when the matter is big enough, I'm going to make this approximation and forget it. So the question does come up, is there a quantum picture for gravity? Yes, there is a quantum picture for gravity, and it's the same kind of business. A thing goes across. We'd have to have a different colored chalk for that, and it's called a graviton, and it would appear in this list except its polarization quality is a little bit different than a photon. It's called spin 2. And the gravitons go back. This picture has it that the gravitons go back and forth. But in any practical situation, there are so many of them that we can use the field theory without thinking about the quantum theory. It's also true that the quantum theory of gravity has infinities like the electromagnetic theory, but they seem to be a little bit more difficult to get rid of. Anyway, that summarizes all that is known by man as far as I knew when I left Caltech before I started to give these lectures. It is always possible that somebody has figured something out in the meantime or measured something in the meantime that I haven't yet heard about down here in the southern hemisphere, which I am enjoying, by the way, very much. And I hope you've enjoyed this talk, and I'm open the situation to lecture to questions. I guess I'll let you ask me questions. I'm done with this lecture.
Could you tell us something about a possible relationship between quantum electrodynamics and gravitation?
No. I don't see it. It's got a long history. You see, at the time when Einstein worked out his theory of gravitation, there's not the quantum theory. It's what's called the classical approximation of field theory. The other important theory in the world at that time was the theory of electrodynamics, also a field theory, not with the amplitude. And so, at that time, the problem was to put always the problem of physics, of put everything together. So at that time, the problem was to put electrodynamics and gravity together. All right? But the electrodynamics and the gravity were both wrong. There should have been quantum theory. And in addition, we find many other things in the meantime. The problem is to put everything together. There's nothing special about trying to put electrodynamics and gravity together, any better than putting quark theory and gravity together, or what? The only one that I know that there's some real advance in understanding how to go together so far is this W meson and photon. That's electrodynamics and weak interaction. The problem is to put them all together, ultimately, and that is the problem I was discussing, and how far we've gotten. It's not very far, but I would not choose, for historical reasons, to think it's more important to put gravity with electricity than to put any other combination together.
Do the correction factors which you mentioned at the beginning of the lecture, and which operate at very short distances, imply that space is quantized?
Yes, that leads to a lot of possibilities. It could be that space is quantized and so on and so on, but all the experiments, you see, are in agreement with supposing that distance is virtually zero. We don't know where it is. It's certainly way beyond the experimental range, which corresponds to 10 to the minus 15 centimeters. It doesn't mean that it could be quantized at 10 to the minus 20 centimeters. But this is an interesting feature. I forget the question. I forgot to repeat the question. The interesting feature is that when people have tried to make a theory that space is quantized, they get into difficulties. Nobody has made up a nice theory that space is quantized that agrees with observation. It's not so easy to make up these theories. What one does all the time is fall into one or another pit. Either you come out that the sum of the probabilities is not 100 of all events is not 100%, or it turns out that you can get states of more and more negative energy. That would be very useful, because what we could do is we could take some object and send it into energy is conserved. The total energy in the world is conserved. But suppose I have this object, I can put it into a place where it has negative energy and get some positive out, because I start, say, with zero. You want more? Put it in a more negative energy. Get more out. So it's obviously an unstable universe if we can have states of negative energy of ever larger possibility. These are the kind of things that happen to a poor individual who tries to make up a theory with some arbitrary thing like a lattice in space or something. He gets into that type of difficulty. There are very few self-consistent theories, and that's the only ones we really know how to write are ones in which we suppose point like space, time, and these propagators with some masses in them, and one or another of the various kinds of polarization systems, either what we call spin zero, spin a half. Spin zero, we don't have knowledge that there are any fundamental particles. Spin a half, all these. Spin one, the photon W and the gluon. Spin 2 is, there is possibility in principle of spin 3 has, but we know of no fundamental particle with that. Spin 2 is the graviton and so on. By the way, there are, it's not the answer to your question, I finished your question, but I must remark that there are many interesting theories which try to put the gravity, electrodynamics, but they always invent a lot new other particles that have to go along with it, such as spin 3/2 fundamental particles and so on. But at the present time, the biggest of them is not able to include the particles we do find and invents a lot of particles we don't find.
Why have gluons not been observed yet?
I didn't completely describe the gluon theory, and don't be afraid, I'm not going to. But just like there were 3 of these coming together, so in the gluon theory there's also 3 of these coming together. I say that not in answer to your question, but to make something I had forgotten to say. This is the place that smokes out as clearly as possible that we don't know how to calculate the most simple thing in this theory. The simplest thing would be, what is the interaction energy between a pair of quarks as you pull them further and further apart? In the case of electricity, the energy it takes to pull a pair of particles apart, the force it takes, goes down fast enough that it takes a certain amount of work and you can get them apart. The question is whether in this theory, as you pull the quarks apart, the force decreases fast enough so that you can do it. If the force stayed constant, no matter how far you pulled them, you could never get them apart. It is believed, hoped is a better word, that if we really could analyze this thing, that would turn out to be the case. Now, the first thing you'd try is to suppose it's the other way. And you find, no, there are terms in here that look funny. It's hard to calculate. It's not so easy to show that the force goes to 0 when they get far enough apart. Therefore, it could be that the force doesn't go to 0 as they get far enough apart. All I'm saying is, the theory is complicated enough that we can't tell. That's why I'm so anxious to figure out how to calculate something. Even the simplest qualitative question as to whether the force increases or falls with distance fast enough or not is not at the present time been analyzed yet from this theory. It's something I think that theoretical physicists should be ashamed of. When you think of how much money is put into doing these experiments and the big apparatus and so forth, and here we just sit around with a beautiful theory and mumble about it and can't calculate any numbers. We shouldn't get our salaries, I think. Or maybe they should be raised. We'd work faster. I don't know.
I'm still worried. Isn't your theory really still a wave theory?
He's worrying about the wave-particle duality that I described in lectures 1 and 2, and says, effectively, that I convinced him that it's particles in lecture 1, and then I did a lot of calculations of amplitude, which seemed to him to be nothing but the analysis of waves, which is the same kind of calculations that we do for waves. And why don't I admit that it's a wave theory that I'm really using? And I tried to explain that in 2 features about it. I chose to talk about amplitude to go from one place to another directly as a given answer. It is also possible to analyze that by saying, and I did say this, that you could think about the amplitude to go from here to here, and then the amplitude to go from there to there. And in that method of analysis, you can write it as differential equations, if you want, a mathematical form that's the same mathematically when you're dealing with a single photon as the Maxwell equations for the wave. There are 2 differences. First, let's take the case of a single photon, in which it turns out that the calculation of my amplitudes is precisely the same mathematically as the calculation of the electric field according to Maxwell's equations, which is a wave theory. The difference is in the interpretation of the answer. The square of the electric field, for example, in that theory, is supposed to be the energy density in space. The square of the wave function, although mathematically determined by exactly the same equations, is the probability of finding a photon. So another way to answer it for the case of single photons is to say this. We calculate as if the light is a wave, but we interpret the intensity of the wave, what used to be called the energy density of the wave, not as the intensity of the light, but as the probability of finding a photon. It's that duality of interpretation which produces the difficulty. Because if this were really a wave coming in, we couldn't understand how the photon counter would acquire enough energy to go off sometimes immediately when you turn it on. No, you see, if, for example, a wave is shining on a surface, a metal surface, we find the following. That if you shine light on a surface and you shine a lot of light, a lot of electrons come out, with each one with a certain energy. If you decrease the intensity of the light, that is, weaken the waves, you would have thought that the wave would kick the electron less, and so you get a lot of electrons out with less energy. That's not what happens. You get fewer electrons with the same energy. And when your wave has gotten so weak it could hardly shake an electron at all, you still see an electron come out with a full jab of energy only once in a great while. And that paradox has to be described by not changing. You see, it would be a miracle if the mathematics would change, because nobody was going to play around with this wave theory that long if it didn't agree with experiment. So there's something right about those equations, the behavior of the amplitudes they were describing. It wasn't interpreted right. First. Second, I've talked about, not sufficiently, and this is a difficulty that many people, I answered somebody else this way, have with this wave particle business and these quantum mechanics, is that the first thing to do when you're giving a lecture is to take the simplest example. And the simplest example is always one particle. But suppose in the same way we take two particles, two photons. I've talked about amplitudes for two photons to come to 2 points. Now the amplitude, if you thought of it as a differential equation, is an amplitude defined. Let's take electrons, or they have 2 electrons. The amplitude defined, if you understand it, I'm writing it mathematically because you were asking me a mathematical question. The amplitude defined one particle at a position in space I'll call x1. It's a vector position. It's a three-dimensional. And the other particle at a position x2, that's a function of time. When there's only one particle, it's a function of x, the position of that one particle, and time. Now, it's characteristic of electric fields, of fields in general, that they're functions of position and time. But when there are 2 electrons or more, the amplitude is the amplitude to find, just like the probability, to find 2 electrons, one here, one there, at the time t. This kind of a function is not a wave. It's a function of 2 positions in space and time. That's a new one. When there's only one particle, it's a function of 1 position in time, then it's like a wave. When there's several particles, the functions or the amplitudes we have to talk about are functions of several positions in space and time. And that's not a wave in the normal sense. And so knowing that that's the case, I emphasize with a slightly different attitude, and I know I'm talking about waves if I was talking about one particle, but not if I'm talking about more. Okay?
You haven't told us very much about quarks and gluons.
It's true that I left out an important thing because of the shortage of time. To make a complete description of these things, I'll just say it, that the quarks of each flavor, like the U-type quark, really comes in 3 varieties. We call them colors, a red one, a green one, and a blue one. They have all the properties the same. They're all the same charge and mass. They're all exactly the same. It's just red, green, and blue. That's 3 different kinds. And what are the 3 quarks that form a proton as 1 red one, 1 green one, and 1 blue one always. Always the 3 different ones. The way the gluons work, just to make a quick thing, I'll be done in a minute. Let's suppose that now I'm going to change the color system and draw pictures with the right colors for the quarks, you see, red, green, or blue. So if I would say I have a green D quark, okay, and it could turn into a red U quark, for instance. And in doing so, it emits a gluon, which I've been drawing as orange, but it's a special kind of a gluon. It's a gluon which has if it went out, a green in it and anti-red. It's like, if to draw it correctly, I should draw colors for it, green and red going the other way. And what happens is if you draw these things, the colors always check out. For example, this could connect to a red, let's say it could be a connection between another quark. Let's say a red D would then turn into a green U or something like that, or a green S or something. No, I'm sorry, you don't change the type. I'm sorry. It has to, with the gluons, you keep the flavor fixed. So this is, say, a U and a D interacting. But the colors get exchanged. What the gluons do is they carry colors back and forth. And the reason why there's a 3 thing is that gluons couple to any kind of color business. So if you have a gluon, which is the green anti-red one, say, you can connect it to an anti-green blue one, for instance. If you emitted a anti-red blue one. So the quarks, the gluons, have colors. And since there are 3 colors, and you have every kind of combination, you would expect 3 times 3 or 9 different kinds of gluons. Actually, there are only 8 different kinds of color combinations. The particular combination, which has an equal amplitude to be red anti-red, blue anti-blue, and green anti-green, doesn't exist. And that describes the theory much more completely than I did before. With that game with the colors, we have a pretty good understanding of why it's only that 3 particles come together, or a quark and anti-quark. Only colorless combinations which are symmetrical in color, that don't have any bias in color, are the low energy states. Any other states presumably take infinite energy to make or something. Can't be made. So you need a red, green, and a blue. You need 3. Okay? Yes. Thank you all very much, and thank Rob for the opportunity to give these lectures. I've often thought I've never been able to figure out how to explain electrodynamics and quantum electrodynamics, and I thought that this was an opportunity to try on a poor, unhappy audience to see whether it was at all possible to explain this subject in a finite number of lectures. And I chose to come to a part of the world as far distant as possible from my home, so that if I were not quite successful, I wouldn't have to suffer so directly. Thank you very much for the opportunity and for your patience in coming all the time to the lectures. Thank you.